Okay, just first of all, thank you very much for having me here. It's always nice to come back to Luxembourg and also, interact with the gang here. And so I look forward to also interacting with the non-Luxembourgish part of the audience. So just, for the record, Adil, maybe I didn't get a prize from Leopoldina, but that's okay.
Okay.
It was a DFT, but it's okay. Just for people, to be clear on these things. So I apologize because my slides will be, partly the same as Alex's slides. Some of them will be even the same slides. The good thing is that I say something different. So that's the...
I think we're sharing the presenter view, so we could disable it.
Okay.
I just don't speak
Okay.
German, like stop the presenter view.
Yes. Okay, wonderful.
Okay.
So...
You don't see it here.
Yes, yeah.
What do I do?
I guess, yeah, we need to
Go back.
go back, yeah.
This one here.
Here. Here.
Now it looks like...
Yeah, I guess we will go with the presenter view for now, and then later for the when we'll upload the YouTube, we'll just cut out the right. Yeah.
Whatever.
Okay.
So I think that I can also just go like this.
Yeah, I think you need to share the screen.
No, but maybe that would be...
Yeah, I think it's okay. Yeah.
Whatever. Okay. So at least you have... So the good thing is I don't have any notes. Yeah. It would be awkward. Anyway, so just before I start, let me tell you a bit where I come from. So I'm with TU Berlin, but also I'm with Bifold, and Bifold is a national AI center in Germany. It's one of 5 national AI centers, and we have the great pleasure that our government has created these, and the funding is on a permanent basis. So of course, all 7 years we have to live up to and defend ourselves, but that's okay. But I think it's a wonderful thing that we have a bit of possibility to think long term. And as you heard from Alex, this has been a long program, and I think it's always if science funding is very short noticed, it's hard to keep track on the long program. So our center has about 22 million budget, so it's kind of nice per year. So that's good, and it's permanent. So I will just try to move forward. Good. So I think you heard a bit by Alex about these things, but I will talk about MD and chemical compound space, but the subtitle in this is how we can use machine learning to gain insights into physics. And just to, as a personal note, I'm actually a theoretical physicist by training. My master was on string theory. And then I decided to go from one obscure topic to another, which at that moment was machine learning. And so that was 89. So it was a bit of a, no one was interested in the machine learning world. And it was only in 2011 that I actually revisited physics, but with a bit more machine learning in the package. And as Alex pointed out, there were 3 of these papers that were setting a starting point to our community. And one was at IPAM, and just, you've heard talk about IPAM many times. IPAM is the Institute for Pure and Applied Mathematics at UCLA. And I got an invitation there in 2011, and I didn't know about this place. So I thought it was a scam, right? So I, I asked, Christian Retsch sent me this invitation, and he said, if you want to talk to someone, how about talking to Jan, because he's your friend, and he will tell you that this is not a scam. And so I was talking to Jan and said, oh yeah, that's a nice place. And then Christian, I talked to Christian, and I finally decided to spend my sabbatical there, right? And in that time, I was thinking mainly about machine learning basics, about brain-computer interfacing, about neuroscience. And then all of a sudden I was in this crowd of chemists and physicists that talked about DFT. And so the first thing for me was, DFT, that's not my discrete Fourier transform that I know from my world. And then I learned about that. And then I thought, isn't it crazy, right? That you start from first principles, and then you make, a lot of transformations, and in the end you make some gross approximation, and then you start doing your thing. And I suggested to instead learn the thing, right? So, which means that instead of, going the DFT path, you would take whatever goes into the equations and just put it into a learning machine, and then use the learning machine to shortcut the Schrödinger equation, which was quite, innovative at that time, because no one at that time was using machine learning to shortcut equations. And it was also not clear whether you could do it. And so the interesting thing is that you could do it, and you see that we have some success in it, and also it became a bit more interesting on the way. So how do we go about this? So first of all, suggesting this idea to a more or less conservative crowd of chemists and physicists and mathematicians was a bit unusual, and they were not happy about it. But then Alex and Anatole and also Matthias Rupp, who was a postdoc at that time, they were all in. So we tried to pursue this. So the first thing in machine learning is always you need to have some kind of a representation. And so you need to compare things, you need to compare objects. In computer vision, it's clear. You take a picture, you have pixels, and you compute scalar products or whatever. How do you do this with molecules? And so the idea was to say, we take a molecule, you have different atoms in the molecule, and you define a quantity which is just the Coulomb force between the ith and jth atom. And instead of having a vector, you have a matrix, right? Because machine learning is not only having vectors, but also matrices, tensors as a representation. So then every molecule would be represented by a matrix, and you could take the Frobenius norm to compute the difference between them. And then we could say, well, why not do something very, very simple? Take this distance matrix into a kernel function. That's a Gaussian kernel. And then we do kernel ridge regression, because it was the simplest machine learning method, nonlinear one, that we could think about. And so at that time, we didn't have millions of examples, but Alex went and tortured the Max Planck supercomputer and got 7,000 data points worth of DFT. And so we used 1,000, and then we trained a kernel ridge regression model, which is very simple because you just have to do an inversion of this matrix that you have. So it takes milliseconds. So now that was the starting point. So the program when the program was finished, we had submitted our manuscript to FISREF letter, and there was some epic battle, because of course everybody thought that this was not physics, but at the end we convinced them somehow that this was physics, and they published it just half a year after the program ended. And that was the precision that how we could learn things was 10 kcal per mole. So that was the first time. So a mean about the data set was about 300 kcal per mole. So it was something. So then we thought life is not about kernel methods. There's other things like neural nets, and then we could reduce this, and we could reduce it some more, and we could reduce it to even more. And one of the things in this was that we use neural networks for that, and the people have always complained that neural networks are not transparent. So if we do physics, we want to have a model that actually doesn't do nonsense, doesn't hallucinate. So how do we know that this is actually true? And this is why we started, analyzing what the models do actually, in order to be sure that things are going well. Okay, so let me just quickly talk about this. So, everybody who's training neural nets or any machine learning models uses this kind of philosophy. You have data, you have a machine learning model, and you would like to predict. So it's not about fitting the data, but it's about trying to make good predictions on data that we haven't seen, and that's called generalization. So there's a fundamental difference between fitting and machine learning, namely machine learning is generalizing, which means that even on data that it hasn't seen, we are predicting well. So now how about things? So there has been, so assume that you have now a machine learning model, and in your machine learning model, typically you have these tables. I personally start hating these tables because machine learning papers are usually full of them, and they're just, they need to be there, but they're not giving any insight, except that you have done your job okay-ish. So let me tell you how to read this table. This is a table from computer vision. We have two models. These models give some prediction about some classes, distinguishing between important things like birds and horses and buses and whatnot, right? So so you see that these models are sometimes have a difference, like the deep net is much better than Fisher for birds, but for the horses you wouldn't see much of a difference. So everything that is reported is always these numbers, and so if you want to understand whether the models are doing some nonsense, then it's important to analyze this properly. So we came up with a method which is called explainable AI. In fact, not a method, but a series of algorithms. And basically, what you do is you have your model, you take some input data, you run it through the model, you get the output, and then you would like to know what of the output of the classification is, why is this classification done in the way it is done? Why is this a horse? Okay, so, and then you need to put the model upside down because it's a nonlinear one. You need to put it upside down, which is a hard mathematical problem, but this was solved. And then you get a heat map of what aspects in the feature vector and the input are important for this very classification. Okay, so let me show you an example. So here, this is a model where we show okay, so this is a horse picture. The model that has been trained to distinguish horses from God knows what is predicting horse for both of these model candidates. And now we have the heat map of why these models actually say this is a horse. So you see here, the horse is considered a horse because of the rider, because of the horse's butt and nose and everything. So because of the object. So that's good. It's a good strategy. Here, this model, you have a bit of the horse's butt, a bit of everything. So red is so to say the salient aspects of the classification. But there's also this part. And I think it's, no one sees this, right? You don't see my cursor, right?
We see it. We see it, yes.
Okay, good. Then you see that there's something going on in this picture which makes the model take the decision, this model take the decision. And it's basically, in this case, it's a copyright tag, right? So there's an artifact in this particular data set, which is Pascal VOC, a historical data set, vintage, so to say, which was accompanying the computer vision community for a decade in all their activities. But since it has many data points, nobody knows about this. No one has looked at all these data points. So it turns out that the horse class has about 50% of the data has this copyright tag, which then a model can make use of to classify a horse. Okay, so you see that this strategy here is the good strategy. That's the object, and here it's an artifact in the data set, and so it's not a good way of classifying. So if we want to do physics, we would like to have models of this type and not of this type. So we would not like to have models that feed on artifacts. So because this was a common thing in many networks, we gave it a name, and so we took another horse as an example. This is the horse Hans from Berlin 1900 something, and Hans was shown by its master math exercises. Hello, Gabor. So then this on this board you see some math problems. So like 3 + 2, right? And the master would point at the respective square, and then the horse would look at this and then take up his hoof and tap to the wooden board. So interestingly, this horse could do the math. So the horse was never wrong. So people concluded from that horses can do math. And because people didn't really expect this, the journalists all over the world wrote horses can do math, which kind of is an interesting and steep conclusion. And then other people came and said, well, perhaps there's something else. Perhaps the horse is actually reading the master. Okay? And so, and they replaced the master by somebody else, but horses can still read humans in general. So the horse was solving the problem of math by solving another problem that has nothing to do with math. So this is why the horse was called Clever Hans. And this is why this kind of strategy, we call this Clever Hans strategy. And a lot of models out there are of the type Clever Hans strategy. So we need to make sure that our models are actually doing something physical and not Clever Hans, because we want to do science and not something arbitrary. Okay, so XAI can reveal the bugs in the machine learning model, discover data flaws, also gives insight to the scientific domain. So you saw this picture from before. That's the DT and N that Alex showed. When we can now analyze how the model is actually solving the problem, and we can inspect that, and you know, that's it would be like some chemical potential in quotes that we depict here, which allows us to look into the model, how the model solves the task. So if you were hydrogen and you would be put somewhere, then this graph, this gummy bear plot, shows you a bit of what the hydrogen would feel, right? Okay, so you can see that this makes chemical sense. Okay, so that's for materials. We can do that as well. I think Alex was already making this point about navigating chemical compound space. I don't have the aspirin configuration in my slide, but I can, you know, sort of remember. So the nice thing about the machine learning part, and maybe I haven't said this explicitly, that if you do this shortcut, you are much faster than existing DFT methods, you know, typically about 30 million times faster. So that is kind of nice if you maintain the quality and of the prediction that you would also get from, and that's out of sample. Okay, so now we change gears a bit and go to molecular dynamics, and I feel, so I have about 20 minutes.
20 minutes,
so.
yeah.
Yes, okay. So I'll speed up and maybe I just so if you think about molecular dynamics, and I don't really need to tell you this, but from a machine learning point of view, this is a bit like a regression problem. So you have the number of atoms. So here we have 5 atoms, and every configuration of these 5 atoms lives in a 15-dimensional space, and you can compute energies and all other quantum mechanical properties. And there's a high-dimensional energy potential, energy surface, and basically if you sample from that and solve a regression problem, then hopefully you get the right potential energy surface. So that's the underlying idea. And perhaps I will skip some slides. So Stefan was there. I was going to show these slides, but maybe Alex was already talking about this a lot. I think the most important thing in the case of GDML or SGDML is that we were able to add knowledge in our models. So we know that energy conservation holds and that molecules have certain symmetries. And so in machine learning, we are learning stuff from data, but there are some aspects that we don't have to learn because there are equations about this. Like energy conservation is a physics equation, so we don't need to learn this. We can put it in our models. Also, the symmetries in a molecule, that can also be put into models. Now, the consequence is that we actually need much less data. And that's one of the perks in GDML and SGDML. And that was a bit surprising to us in the beginning, because if you think about the aspirin configuration and the energy surface that we sample, we typically need about 50,000 data points. And if we take into account energy conservation or the molecular symmetries, then all of a sudden we can find a formal equivalent model with much less data, which is in this case 100 instead of 50,000. So which means that perhaps we can afford some higher order theory calculations so that and do, instead of DFT, we do CCSDT, and then we have a much higher accuracy. So enabling that was a very important part of GPML. Now, there's of course, as you may have read, some discussions about whether you would put in a priori knowledge explicitly or not, in particular in the context of neural networks. Because if we think about this, it's not a simple thing. So once we put constraints can make the optimization process much more complicated. So then there may be the learning problem gets harder. While the constraint is a good thing, the learning problem gets harder. If the learning problem gets harder, then it takes much longer to converge, and maybe we find less good solutions. So there's actually a very practical trade-off that we should be aware of about putting constraints explicitly or implicitly, or just by learning and then finally putting constraints. So that's an open discussion, and the paper by Max Eisler and co-workers actually were studying this. If you don't put any constraints and a lot of data, how far do we get? And interestingly, we get far, but there's limits, stuff that we cannot do. So ultimately, we will need the constraints. So I think it's an interesting study, although one of the referees said, this should be forbidden to do studies like this, because we know that physics exists. Why would you do something without any, constraints? Anyway, it's unphysical, right? So, and I sort of agree, but I also disagree, because, I think it's important to understand, how far we can get, because that allows us to do new generations of models, okay? So we heard about SpookyNet, and just to add, it's the first transformer that was being used in quantum chemistry. It's not the first transformer that was done by Jakob Uskureit and co-workers. Jakob, by the way, was a master's student in my group at some point. Okay, so we were the first to use a transformer in quantum chemistry, and this is like the block kind of pictures that you show on these occasions. If you don't show equations, I think it doesn't make sense. But just showing this means that there's something that you can read out. So there's Oliver Unke, who was the leading figure in this, and we've seen Oliver Unke's face already in Alex's slide. That I think it's interesting to really take a quick look at what we did at that time. And I think Alex already explained this a bit, but the situation was that we were all grounded because it was Corona. And so I was sitting on my sofa, and Alex was sitting on his sofa, and everybody else as well. So, and we wondered what the heck should we do, because just sitting on the sofa is not fun, right? So we needed to have something. And so at some point we wondered, how about trying to do a force field for a very large system, like the receptor binding domain for the spike protein, because somehow this was important for that at that moment. And but then, thinking about it, if you would take a accurate force field for a system with, say, 100 atoms, then this would be something like 4 weeks of compute. But if you would now go to a 10,000 plus atom system, like this spike protein, then and you consider the scaling of these algorithms, then this would be like something like 4 weeks that you have already for a 100 system, and then times 100 to the 5, which would be the compute to get one data point essentially, which is something like age of the universe kind of compute. So even at Google, people wouldn't have that kind of compute, and I wouldn't have age of the universe time for obvious reasons. So then we thought, how can we do this without going into this trouble? And so the idea was to say, let's take our new SpookyNet transformer architecture, put a lot of physics knowledge, and then put a lot of data, and then follow the following idea: do local, do force fields for smaller systems, and then, stitch them together, like in a patchwork blanket, like this one here. You would stitch things together, but then, then you would have a local model, and the local model is good enough. Alex taught us that van der Waals is so important, right? So long range is important. So we need to also learn the long range part in some way. And this is why we took not only, larger fragments, not only smaller fragments of data for our training, but also took progressively larger fragments. And in this way, we would hope to learn also the long-range aspects. So that was nice, and I think you may have seen this before. There's this, okay, I think I will have to. So here is a simulation for this adenine 15 lysine by this novel algorithm, and you can see how this folds. This is in vacuum, but you can see that it's a nice kind of exercise, but it's actually interesting because it shows that this folds into a helical structure, but a close inspection also shows it's alpha helix and 310 helix that alternate, which was something that was not so expected, and we thought that perhaps there was something wrong, but there was nothing wrong, and experimentally this was also observed. It's just that classical force fields don't observe it because they have the alpha helix in their genes, so to say. So just to show you this again, so we took a lot of small fragments, we took a lot of large fragments, then we did this patchwork thing, and then you saw the folding dynamics, and of course this was an exercise for the adenine 19, but we can also measure the accuracy, and we see that as expected to a classical force field, we're more accurate, and we can also see different structural fluctuations in this approach, different from the classical force fields, but more similar to the NMR solution. Okay, so let me also move forward. There's the Socrates, which is again the basic ingredient. That's the model, the backbone model of solar. And while Alex was showing that the equivariance is an important ingredient to make molecular dynamics not only stable but also accurate, but also it makes it very slow, right? So any equivariant model is slow at that moment. Therefore, we had this idea of this, separating this invariance and equivariance thing. So again, there's the blocks. Maybe more interesting is the kind of scaling that we experience. So we would, in NeQuip have something like this Lmax plus 1 to the 6 times f, and in Socrates we have this. There's a square, but this is plus f. So you can already read from this form, from the compute order, that Socrates has the chance of being much faster. And so the secret sauce in this is again that we are separating the invariant and the equivariant part, and in this way we are actually saving a lot of compute without losing any accuracy. And if you look at frames per second, so on this side that's speedy, and that's the accuracy. So low is high accuracy is a good thing. So that's that's the mean absolute error. So the accuracy gets better if we are low, and so you see that there's a trade-off in this. So it's an accuracy-speed trade-off, and you can see the usual suspects, and one is sticking out. That's Socrates, and that's also a lot of machine learning people have been seeing quantum chemistry as a way to generate tables with benchmarks, and they have just found better and better models that predict forces and energies better. And then at some point someone came and said, well, I think it was Tomiakula, who said it's totally irrelevant because molecular dynamics is about running long molecular dynamics trajectory that are stable and physical. So it means that we also have another aspect. It's not only the speed, but there's also the stability that is important. So we know that NeQuip and the equivariant methods are actually on the sweet spot in terms of stability, but not in terms of speed. But Socrates is, so to say, taking the best of all worlds. Okay, so then we can do stuff with it, like the buckyball catcher. So there was the question about the speed, and that's already, it's 3 years ago. So at that moment, we could do 20 nanoseconds within 64 hours of our time. So now the GPUs are a bit quicker and everything, and so that number will be much lower. Okay, so there was another aspect which has appeared this year. That's the Euclidean fast attention. So if you have a transformer, then the problem is if you want to study interactions on a more global scale, then if in principle we could not have a cutoff, right? But that, of course, gives us two problems. The data that we have will become very, very sparse. That's number one. But also, if you want to do any kind of attention mechanism, then this will be a squared algorithm. It runs as squared. So in this case, anything that would be reasonable needs to be linear scaling. And this Euclidean fast attention is a new mechanism how to basically have no cutoffs and still do linear scaling attention. And this is a mechanism that we can plug into any of the methods that is out there. So it's orthogonal to just having a new model. It's just a new part of the model that we can plug in, right? Okay, so then we saw that the hero sits in the row and harasses me about time. So we've seen we can navigate chemicals compound space, we can have very accurate force fields, but now we can have universal force fields, and universal I put in quotes because I think they are so far, they have their limits and we should be honest as a community. But this is a very nice one because we can see that this foundation model that Adil and Torben did, which is based on the Socrates backbone, is actually very powerful and works for many aspects of chemistry out of the box. And that is, I think, a very great progress, because I was told that even if you would come up with a new classical force field, then typically you would take 1/3 of a PhD student to really have it nice for a new system. That's what I was told. So here you just run it and have the high accuracy of the machine learned force fields. So now I'm coming back to this explanation stuff, okay? So I hate to spoil the party, right? So a lot of us are using foundation models, and any of the foundation models are always trained with self-supervision, right? So anything that you're using is using self-supervision. Now the problem in this is that, and that's the background of this paper. I don't have the time to go into this, according to Adil, but there's a very important thing to worry about. So if we train a foundation model with unsupervised techniques like self-supervision, it could happen that this foundation model is also of the type clever Hans. And this is what we showed. And it's in the case of the clever Hans, the horse pictures that I showed, it was an issue, a bug in the data. There was copyright tags, there was some artifacts in it. But here, it's a bug in the machine learning itself, in the training. And I would just give you an intuition about this. But this was something that came very unexpected to me. So we know that in supervised learning, and this is just a cartoon, in supervised learning, we have some regression, say, and so you have data points, and you could just fit this with a green line, and that's called overfitting. So if we generalize, we are not fitting, but we are rather taking a good fit like this orange curve. This is what machine learning does. Underfitting would be the blue curve. Now, if you do any kind of foundation model training, it's always using one way or the other unsupervised learning. And what you actually see is that, if you analyze it carefully, is that unsupervised learning is also prone to overfitting. So that's a very fundamental insight, which means also that if you don't implement the unsupervised learning part of your foundation model correctly, it will just do clever Hans, and anything that you do downstream will inherit this clever Hans. So, and the idea, I think, is very simple. So assume we do some kind of a simple unsupervised learning algorithm. Like here you would have just some distribution and you do density estimation. So if you do density estimation and you're using the wrong bandwidth, too small bandwidth, then it's overfitting. That's the green curve. So if you regularize a little bit, then it's the orange curve. So if you regularize a little bit in your unsupervised learning training of the foundation model, then you won't have the overfitting. You won't have the clever Hans. This is really the take-home message for you. So you already saw that we generated a lot of data. That's the QCML data, and I believe many of you are already using it. And then I come to my conclusion, which is basically all these models learn to represent the chemical environment, including prior knowledge is superbly helpful, but we have to be aware of the, if we formulate this, depending on how we formulate this, it can also harm the optimization process. We have to be careful, and there's no, magic bullet to solve this yet, but we are thinking about this. It's very important to have short-range and long-range interactions. Just being short-range doesn't help in most systems, but it's hard to actually incorporate long-range. And the true challenge is to be insightful when you use your foundation model for chemistry. What do you learn new about chemistry? I think that's the interesting thing. And XAI, explainable AI, is a very important technique with which you can study these models that we have. And just be aware, clever Hans is not only in supervised learning, but also in unsupervised learning. So if you don't regularize properly, then this will mess up your foundation model. Thank you.
So we have time for maybe 2 questions or 1 question. So I can read one from the chat. So Sandeep Mandal is asking, but in case of proteins, do we need to consider solvent-water interactions as well? Because then the degrees of freedom will be very high. And this is to your point, like 100 to the power 5, I think.
Yes, and so maybe I didn't spend enough time to show you. So see these red things, these little red things. That's called water. So I mean, I remember. I think it's a very important and valid question. So we always have to consider things in solvent, and this is why the foundation models are always considering solvents around them. So even the GEMS model was taking crumbene in water. You may debate whether crumbene in water is very sensible thing to look at, but still it was in water, so that was 25,000 atoms. Okay?
Okay, thank you. So we will...
Anyone else? Yes.
So in the direction of explainable AI, so in tree-based models, people use, for instance, a sharp analysis to understand which descriptor is more relevant. Here it's possible to do something similar, but to understand which interaction is more relevant or which chemical motive is more relevant. So.
Yes, the answer is yes. So the technique, I didn't go into details on this. So the explainable AI field was a bit similar to this field that we are just enjoying. So I wrote my first paper in explainable AI in 2010, and that was perhaps one of the first papers ever in the field. And then in 2015 there was the layer-wise relevance propagation, which was way before the SHAP. So I think so layer-wise relevance propagation is a family of algorithms that is very useful, but there's also SHAP and others. So my point is not to advocate layer-wise relevance propagation. Of course, it's dear to me because I happen to be on the paper, but there's a zoo of possible methods that we can use. But the point is, we need to really scrutinize our models. And if we don't do this, then there will be clever Hans, whether this is in a foundation model or whether this is in a supervised training model. So we always have to carefully analyze this, because otherwise we cannot be sure whether this is physics or not. And so one of the, just to expand on this a bit more, one of our joint studies was, trying to analyze why the stability of some models is not so great. And so in that case, we used some technique by Malte, Estes, and co-workers, which try to understand the interactions in molecules and see whether the models that we're using are reflecting the physics of proper interaction, like that we would expect. And interestingly, once the interaction was according to the physical laws, this was also a stable model in terms of MD. But if it was underfitting or overfitting, it was not. So that's one additional aspect to equivariance that we can take care of.
Okay, thank you.